You think stars die. That is the first mistake. Stars do not simply die. They transform violently, magnificently, inevitably into something the universe needs far more than another burning sphere of hydrogen. And here is the truth. No textbook ever handed you with the weight it deserved. Every atom of iron in your blood was forged inside a star that had to destroy itself to give it to you. Not metaphorically, not poetically, literally. The iron flowing through your veins right now, the same iron that carries oxygen to your brains and comprehend these very words, was synthesized inside the core of a dying star billions of years before this planet existed, before ocean, before continents, before the first single-celled organism dared to breathe. You are not made of stardust in the way a greeting card would have you believe. You are the direct consequence of stellar death. You exist because something magnificent ceased to exist first. So when someone asks, how do stars die? They're really asking something far more personal. They are asking, how did I come to be? Now, let us begin properly. Close your eyes for just a moment. Imagine you are holding a match. Strike it. Watch the flame appear small, trembling, alive in a way that seems almost impossible for something so brief. That flame is burning because it is releasing energy stored inside chemical bonds. It is consuming itself to produce light. It gives everything it has, and then it goes dark. Now, scale that image up, not 10 times, not 1,000,000 times. Try 2 octillion times. That is roughly the mass of our sun compared to a matchstick. And our sun is, by cosmic standards, a rather ordinary, medium-sized, unimpressive star. There are stars out there so massive they make our sun look like a candle flame next to a forest fire. Every one of those stars is burning. Every single one is locked in a battle that has been raging since the moment it was born. And every single one will lose. The question is how they lose, because that, as it turns out, is the most important story in the universe. Here is what most people never stop to consider. A star does not burn because it wants to shine. A star burns because it is terrified of collapse. That is not a metaphor. That is physics. From the very first second of a star's life, 2 forces are locked in a battle for absolute dominance. Gravity, the great compressor, the force that pulled all that gas and dust together in the first place, wants to crush everything inward. It wants to collapse the star into a single, infinitely dense point. Gravity is patient. Gravity is relentless. Gravity does not negotiate. But pushing outward, fighting back with every ounce of force it can generate, is radiation pressure, the energy released by nuclear fusion happening in the star's core. Every second in the heart of our sun, 600 million tons of hydrogen are being fused into helium. 600 million tons per second. And the energy released by that process pushes outward hard enough to hold gravity at bay. This balance, this constant violent standoff between collapse and explosion is called hydrostatic equilibrium. And it is quite literally the only reason stars exist at all. But here is the philosophical question I want you to sit with. What happens when the fuel runs out? What happens when a star has burned through everything it has, when there is nothing left to lose and gravity finally wins? That answer is not simple. It is not the same for every star. And it is, without question, the most consequential process in the observable universe. In the next section, we go inside the core, we watch the fusion process fail, we follow a star into its final hours. Picture a baker. Every morning, the baker arrives before dawn. Flour, water, yeast, ingredients transformed by heat and time into something nourishing. The bakery is warm, it smells of life. People walk past and feel, without knowing why, that everything is going to be fine. Now imagine the bakery is running out of flour. It does not stop immediately. The baker finds old reserves, switches to different grains, adjusts the recipes, but with each adaptation, the bread becomes slightly different. The warmth remains for now. The light in the windows stays on. From the outside, nothing seems wrong. That is precisely what a star does in its final stages of life. And like the bakery, the end, when it finally arrives, comes fast. Let us talk about what fusion actually means inside a stellar, because this is where most explanations lose people and where the real wonder lives. Stars begin their lives fusing hydrogen into helium. This is the comfortable, long phase, the main sequence. Our sun has been doing this for approximately 4.6 billion years and has roughly another 5 billion years remaining in this phase. Hydrogen fusion is clean, efficient, and produces staggering amounts of energy. But hydrogen is finite. As the core accumulates helium, the ash of hydrogen fusion, it begins to contract. The helium does not fuse easily. It requires far higher temperatures and pressures than hydrogen. So the core contracts under gravity, heating up until eventually those temperatures are reached. Then helium fusion. Helium fuses into carbon and oxygen. Now the star has entered a new phase. It has found new flower, so to speak. But helium burns faster than hydrogen. The timescales compress dramatically. What took billions of years for hydrogen now takes only hundreds of millions for helium. And then the helium runs out. What happens next depends almost entirely on one single variable: mass. For a star like our sun, which astronomers classify as a low to medium mass star, the story ends relatively quietly. When helium fusion fails, the core contracts again, but this time the temperatures and pressures reached are not sufficient to fuse carbon. Carbon fusion requires conditions so extreme they only occur in the most massive stars in the universe. So our sun will reach a kind of threshold. It will swell into what we call a red giant, expanding so enormously that it will likely swallow Mercury, Venus, and possibly Earth itself. Then it will shed its outer layers in a beautiful glowing cloud called a planetary nebula. The core that remains, a dense, hot remnant of carbon and oxygen, no longer fusing anything, is called a white dwarf. A white dwarf is, in the most precise sense, a dead star. It produces no energy. It simply radiates the heat it has stored, cooling over billions and billions of years, until eventually, over timescales so vast they exceed the current age of the universe, it becomes a cold, dark object called a black dwarf. There are currently no black dwarfs in existence. The universe is not old enough for any white dwarf to have cooled that completely. Every white dwarf that has ever formed is still glowing. Think about that for a moment. Every star that has ever died in a quiet, dignified way, every stellar corpse produced by a low-mass star is still warm, still radiating, still giving something to the cosmos, even after the fire has gone out. Is that not exactly what we hope for ourselves? But now we must talk about the other kind of death, the violent kind, the kind that shakes galaxies, the kind that seeded the universe with the elements that built your hands and your eyes and the neurons firing right now as you process these words. For that story, we need a massive star. We need something at least 8 times the mass of our Sunday, something that does not go gentle, something that goes supernova. There is a particular kind of silence that arrives just before something enormous happens. You have felt it, standing at the edge of a cliff before jumping into water below, the moment before a thunderclap, the held breath of the universe in the instant before it speaks. Massive stars, those behemoths, 8, 20, even 100 times the mass of our sun, live their lives a state of constant, furious, urgent. They burn brighter, hotter, and far faster than quieter stars. A star 100 times the mass of our sun may live only a few million years. Our sun, by comparison, will live 10 billion. The most massive stars burn through their hydrogen in the cosmic equivalent of a weekend. But because they are so massive, they do not stop at helium fusion. They have enough gravitational pressure to push through barrier after barrier of nuclear physics. Helium fuses to carbon, carbon fuses to neon, neon to oxygen, oxygen to silicon, each stage faster than the last. The timescales become almost incomprehensible in their compression. Hydrogen burning, millions of years. Helium burning, hundreds of thousands of years. Carbon burning, perhaps 1,000 years. Neon burning, roughly a year. Oxygen burning, months. Silicon burning, 1 week. 1 week. In the final week of a massive star's life, its core is fusing silicon into iron at temperatures exceeding 3 billion degrees. The star has developed a layered structure like a cosmic onion, with different elements being fused in different shells surrounding the iron core. And then silicon fusion produces iron, and everything stops. Here is why. And this is one of the most beautiful and brutal facts in all of physics. Iron is the most stable element in the universe. Fusing iron does not release energy, it absorbs it. Iron fusion is energetically impossible in the way that falling upward is physically impossible. You cannot get energy out of iron fusion, period. The moment a massive star accumulates an iron core above a certain critical mass, approximately 1.4 times the mass of our Sun, known as the Chandrasekhar limit, the core can no longer support itself. Radiation pressure collapses, gravity, which has been waiting billions of years for this exact moment, wins. The core collapses, not slowly, not gradually. The entire iron core, a sphere roughly the size of Earth, collapses to an object the size of a city in less than 1 second. In that fraction of a second, densities are reached that are almost theologically incomprehensible. Protons and electrons are forced to merge into neutrons. The collapsing core rebounds a bounce so violent it sends a shock wave outward through the star at a significant fraction the speed of light, and the star explodes. This is a core collapse supernova. The energy released in those few seconds exceeds the energy our sun will produce across its entire 10 billion year life. The light from a supernova can outshine an entire galaxy of hundreds of billions of stars. For weeks, a single exploding star can be seen across the observable universe. And in that explosion, in that spectacular act, stellar self-destruction, every element heavier than iron is forged. Gold, silver, platinum, uranium. The heavy elements that make up your jewelry, your electronics, your medical instrument, synthesized in the last seconds of a dying star's existence and flung outward into space at millions of kilometers per hour. Scattered across interstellar space, eventually gathered by gravity into new cloud, new star, new planet, new biosphere, new people, you. After the supernova, the universe does not clean up after itself. It leaves remnants, monuments to what existed, evidence of the violence. What remains at the center of a collapsed massive star has one of two possible fates, determined entirely by its mass. If the remaining core falls between roughly 1.4 and 3 solar masses, it becomes a neutron star. If it exceeds that threshold, nothing in the universe can stop the collapse. It becomes a black hole. Neutron stars deserve far more attention than they typically receive. The densest objects we can actually observe, they are composed almost entirely of neutron, packed so tightly that a single cubic centimeter, roughly the size of a sugar lump, would weigh approximately 1 billion tons on Earth. 1 billion tons in a sugar lump. These objects are typically 20 kilometers across. You could drive the full diameter in 15 minutes on a highway, assuming the gravity 200 billion times stronger than Earth's would not compress you into something thinner than paper long before you arrived. When a massive star collapses into a neutron star, conservation of angular momentum causes it to spin with extraordinary speed for the same reason a figure skater accelerates when pulling their arms inward. A star that once rotated slowly over weeks can collapse into a neutron star spinning hundreds of times per second. Those that emit beams of electromagnetic radiation from their poles, like cosmic lighthouses sweeping the darkness, are called pulsars. Some are so precise in their rotation they rival atomic clocks, cosmic timekeepers born from cataclysmic violence. And when two neutron stars orbit each other, spiraling inward over millions of years and finally colliding, the event is called a kilonova. These collisions distort the fabric of space-time, produce gravitational waves detectable across billions of light years, and synthesize vast quantities of gold and other heavy elements in fractions of a second. The gold in your ring was likely forged in the collision of two dead stars. Not poetically, literally. When the remnant core exceeds 3 solar masses, nothing stops. Matter collapses past the neutron star stage into a singularity, theoretically infinite density, where our current physics simply stops working. Surrounding it, the event horizon, the boundary where escape velocity exceeds the speed of light, cross it, and the universe you knew is gone forever. And yet black holes are not endings. They feed, they merge. The supermassive black holes anchoring entire galaxies may be the very reason those galaxies exist in the form they do. Death, it seems, is never simply an ending. Now, here is what I want you to carry with you. Not the terminology, the implication. Every element that makes biological life possible, carbon, nitrogen, oxygen, phosphorus, iron, was synthesized inside a star. The pathway from the simple hydrogen and helium of the early universe to the complexity of a single living cell required stars to be born, to burn through every element they could reach, and then to die violently enough to scatter those elements across interstellar. Life is only possible because of stellar death. That is a precise scientific statement, not a poetic. You are the universe's way of knowing itself. More specifically, you are the product of stellar sacrifice across timescales so vast they should make your sense of self feel simultaneously infinitely small and cosmically significant. Stars do not choose to die. They follow the laws of physics with total, non-negotiable compliance. Gravity wins because gravity always wins. There is no rebellion, no negotiation. The star simply becomes what the physics of its situation demand. And yet from that complete surrender emerges every mountain, every ocean, every face you have ever loved, every thought passing through your mind right now, every moment of connection between two human beings who found each other briefly in the dark, all of it traceable without interruption back to the death of stars. The universe is still making stars tonight. In nebulae across every galaxy, gravity is gathering gas and dust into new stellar nurseries. Stars being born right now will burn for billions of years, die, and scatter elements that may one day form planets, oceans, and forms of life we cannot yet conceive. The process that built you is still running. The universe does not waste a single atom. It transforms always, endlessly, toward greater complexity, greater strangeness, greater beauty. You are not separate from this process. You are not an observer standing outside it. You are the cosmos, temporarily arranged into a configuration capable of asking why, and that question may be the most extraordinary thing any arrangement of matter has ever produced. The stars do not care about you, and yet here you are, assembled from their deaths, warmed by a living star's ongoing fusion, existing briefly and brilliantly on a pale blue dot in an unremarkable galaxy, in a universe whose full scale you will never live long enough to comprehend. The least you can do is look up. The least you can do is wonder.